Welcome back. So in this lesson we are going to discuss the US arrests dataset, and from there we can also discuss the Biplot, right? And we will understand why we need the Biplot and how to read it, right? It's very important for the PCA. Now we have a dataset called US arrests. It's available on Kaggle, and I will leave the link in the resources, right? So if we check this dataset right here before doing anything, right, after just reading it using pandas, you will see that we have something like this, right? So we have a column called unnamed 0, and it contains the city, right, or the state, and we have here murder, assault, urban population, and rape. So we have how many features? We have 4 features, okay? And as you can see, the murder rate or the values are basically very low compared to the assault, for example, right? So basically this dataset contains statistics in arrests, that's why it's called US arrests, per 100,000 residents for assault, murder, and rape in each of the 50 states in America in 1973. Also we have another column here called the urban population, right? This is the percent of the population living in urban areas, right? So we will perform some very basic pre-processing. So we are going to just drop this column, right, and have it in a variable called names, right? So we have a series here called names that contains Alabama, Alaska, Arizona, and so on, right? So you will drop it. So it would be much easier to do any pre-processing or do any visualization or whatever using this dataset. Okay, so the full dataset we have after that is basically after dropping this label in place, we have this data, right? Murder, assault, urban population, and rape. So what we are going to do first is that we are going to scale the data, and we will discuss scaling in the next lesson. So we'll use the standard scaler from sklearn. We are going to fit, we are going to transform, and then we are going to define the PCA sklearn, right? This is from PCA implementation of sklearn, right? We are going to use their implementation in this part, and we are going to use fit transform on the original dataset. So we will have xnew. This is basically the data after transformation, and if you notice, we didn't really specify any hyperparameters here. So if you check here, you'll find that for the parameters, the number of components can be an integer, float, none, or string, okay? If number of component is not set, all components are kept. So this is basically very important. So if you didn't really specify how many components we want, it will just leave all the components. Okay, so this can be a little bit weird, right? But this is how it works. And number of components is basically equal the minimum of number of samples or number of features. So most probably the minimum of features will be much less than the number of samples, right? And this is basically how this algorithm works. You can check the documentation more if you are interested to know how it works. Okay, so this is all the hyperparameters we have. All these hyperparameters are not important at all, right? This is for the implementation itself for sklearn, for making the code much faster. But for example, you can see here that svd solver is equal to auto. So by default, it will use the numpy linear algebra singular value decomposition in order to get the eigenvalues and eigenvectors and so on. And we have copy equal true in order to copy the dataset and so on, right? You can read the documentation, but it's very straightforward to use the PCA from here, right? And then we are going to use the fit transform in order to reduce the dimensionality. Now we have a very important concept for sklearn, or a very important plot for sklearn called the pie plot, right? So the pie plot is basically, we give it the scores, the coefficients, the names, and the label. This is my implementation or our implementation for this function. But before going into the details of this implementation or the implementation of this function, let's run it, right, and see what we will get and try to understand the plot itself. And then we will go back to the code and read the code step by step. So if we run this, you will see that we have here df is not defined. So if we check here, you will see pie plot xnew transpose. Yes, we need to have here df, what we called it df arrest, right? So if we run this now, you will see that we have another error because we converted this to a numpy array, right? We converted this data frame into a numpy array when we did this transform, right? So what we need to do here in order to have a trick, right? We can just create a copy of this, right? So let's call it df equal, right, df arrest. So if we do this and come here and just write df.columns, what do you think will happen? It will run, right? So let's take a look at the output and then we will discuss the code, right? So here we have the first principal component and the second principal component, and these are the states, right, visualized in 2 dimensions. So if we reduced the dimensions into 2 dimensions, okay, so instead of 4 dimensions, originally we had 4 dimensions: the urban population, the rape, the assault, and the murder, right? So if we check the new data or mapping the data into the 2 dimensions, you will see that we have these 4 things, right? These 4 arrows and or lines. If we check them, let's take a look, for example, at the first principal component, right? It's the first principal component in this direction, right? So if we check murder, assault, and rape, you will see that all of them are in the first dimension direction, right? So if we go into this direction, this is the first principal component, and as we can see, the assault is very, very close to the first principal component direction. The same for the murder and the same for the rape, right? So this makes sense because the murder, assault, and rape are actually very correlated. So if we have a state that has a high rate of murder, most probably it will have a high rate of, and so on. On the other hand, the urban population is not related to these 3 dimensions, right, or these 3 features. So that's why, as you can see, the urban population is much closer to the second principal component, right? If we have the second principal component in this direction, the urban population is very, very close to the second principal component, and it's very, very far from the first principal component. So this is the first finding we can get from this plot, right? Let's discuss another thing. Let's discuss the placement of the states, right? So let's check something like Nevada, for example, right? So if we go to Nevada and check Nevada, right? So if we go here and just print df arrest, you will see that we have for Nevada, if we go to Nevada, this is Nevada, right? So let's go to the assault rate. So as you can see, if we go to the assault rate, or let's go to the rape rate first, right? So let's go to the rape rate. You will see that it has 46 rape rate, right? So if we take a close look, you will see that this is the highest rape rate in all the states, right? So Nevada placement is actually not just random, right? It's very, very, very correlated to the rape. So that's why the rape is in this direction, because Nevada has the highest rape rate. While on the other hand, if we go to Vermont, for example, so if we check Vermont, let's go to Vermont, you'll see that Vermont has one of the lowest rape rates, right? So it has 11.2. It's one of the lowest rape rates, right? So this is a clear sign that rape is correlated with Nevada, and it's highly uncorrelated with Vermont, or it's negatively correlated with Vermont, right? Now let's go, for example, to Alaska, right? So let's go to Alaska. So if we check Alaska and check the murder rate for Alaska, you will see that for Alaska the murder rate is 10, right? And this is also one of the highest rates. So let's check the highest rate. It's Georgia, right? So let's go to Georgia and see where Georgia is placed. As you can see, Georgia and Alaska, right, are placed near each other, and they are correlated with the murder. If we go to the assault, you will find that Maryland and New Mexico are highly correlated with the assault, so they have the highest assault rates, and so on. If we go to, let's see, the urban population, right? So if we go to the highest urban population. Let's check here which one has the highest urban population. I think we'll see that California has the highest urban population, 91, right? So if we check here, you'll find that California, right, is much closer to the second principal component than the first principal component, right? Because it's correlated with the urban population. It has the highest urban population, right? If we go to Vermont and check the urban population for Vermont, for example, you will see that Vermont for the urban population is one of the lowest, right? It's 32. It's almost the lowest, right? Because here, this is the direction of the second principal component. This is the direction of the first principal component. So it's not related to the second principal component or the first principal component. It has like a negative correlation or dependency between these two, right? So it has one of the lowest urban population, and it has one of the lowest assault rates, rape rates, and murder rates. So this is basically how you can read this pie plot. So how we do it, we just have the first principal component, the second principal component. We plot the data just like before. I just have the labels right here in order to make sense. And then we plot the features themselves, right? So we plot the features onto the new dimensions, onto the new space, right? The original features onto the new dimensions. So how we can do so? Let's take a look at this pie plot. So first we need the score, right? So the score is basically x in u. This is basically the data after transformation. And we take only the first two columns, right? So the first two columns of the new transformed data. So we have 4 new principles. We will take the first 2 principal components. Okay, and after that we will get the coefficients. So how we can get the coefficients? We have inside PCA sklearn something called components underscore. So this is basically the coefficients of the basis functions, right? So as we said, if you remember at the very beginning, we said that we can construct any example using b1 times u1 plus b2 times u2. And we said that u is basically the principal components and b is basically the coefficients or the components themselves, right? So this is why we have here coefficients, and the labels or the names are the names of the states, right? The labels are the list of the columns names, right? So the labels are the murder, the assault, the rape, and the urban population. This is the input for this function. So what we are going to do is that on the x-axis, we are going to have the first principal component. On the y-axis, we are going to have the second principal component values, right? And then we will get n, right, from the coefficient shape. And after that, we will get the scale for x and the scale for y by just dividing 1 by the maximum minus the minimum, right? This will get the scale, how many values we need. Okay, and after that, we will just have our own plot, and we will use the scatter plot, right? So we'll use the scatter plot. What we are going to have on the scatter plot is basically the values times the scale, right? In order to have the values scaled properly, and we can see exactly what's happening, right? And after that, in order to have these names on the plot, we are going to use the enumerate function, right? So we're going to get the names 1 by 1, and at the same time we are getting the count or the iterator, right? So 1, 2, 3, 4, and so on. And the text is basically the current state name. So we have a function inside AX, right, from PLT or Matplotlib called annotate. So we're going to use this function. We are going to annotate the text where we want to annotate it, here, right, or here, or here. So where exactly? Basically, the current position, right, x, si, the current position, times the scale, because we are using the scale. For the x and for the y, the same story, right? So now we have the plot, and we have this plot, and we have the values, and we have the names. Now for the red plots, how we can do it? We can just loop over I for range n. So n is basically the number of dimensions originally, right? And we are going to have an arrow right? From AX also we can have an arrow. Okay, and you can check the documentation for this arrow, and the documentation is just saying you can have the color, we have red, and the position is basically coefficient, right? So the coefficient I0 and I1. So I0 will return the X position, I1 will return the Y position. Okay, that's pretty straightforward. And if the labels is none, so if you are not using any labels, then we are going to do something just like this in order to have variable 1, variable 2, variable 3, and so on. But if we have the labels, if we have like a list containing the labels, then we are going to have a x.text, just like before. And now we are going to have the labels just a little bit further from this arrow, right? So that's why we are multiplying by 1.15, and we are going to have the text equal to the labels I. So each time we get the label, and that's it. And the color is green, and center, the vertical position and or vertical alignment and horizontal alignment is center. So that's why you see it's pretty simple. And then we set the limit, the x limit and the y limit, to be between -1 and 1. We can have it, for example, between -0.5 and 0.75, for example, but that's okay, right? And that's it. We set the labels to be PCA1, PCA2, and that's it. So that's how we can plot the Biplot, how to read it, and how to understand it. And this function, it's not like new. I didn't really write it myself. I just edited this function, but I will leave in the resources also the Stack Overflow question that was asking about how we can implement the Biplot from scratch in Python, and I will leave you this link and you can check the answers, and this was one of the answers, one of the best answers. So I wanted to explain to you how you can do the Biplot yourself, but most importantly how you can read the Biplot and get information from this Biplot, right? So in the next lesson we will discuss the effect of feature scaling on PCA, and at the same time we are going to discuss the scree plot, one of the most important plots for PCA. And that would be a very interesting lesson, so let's go and see it.